You may have heard of superconductors before. Indeed, we even saw a mind-blowing application of superconductors in the first lecture of the course with a magnetic levitation device. But what exactly are these superconductors and how were they discovered? Superconductors are materials that can conduct electricity with little to no resistance. They came to be discovered in the early 1900s when physicists, armed with the knowledge that the same material has higher resistivity at higher temperatures, wondered how low of a resistivity they could achieve by seriously cooling the substance. Then it was Dutch physicist Heike Kamerlingh who cooled some mercury to about 4 degrees Kelvin, ran a DC current through it, and noticed that the resistance completely disappeared. He had discovered the first superconductor. Now, what is the underlying physics behind superconductors that makes this phenomenon possible? It turns out that when we supercool electrons, their quantum states, or eigenmodes as we learned in class, start to overlap and form something called Cooper pairs. This single quantum state that the Cooper pairs are in is known as the Bose-Einstein condensate. The condensate forms when the de Broglie wavelength, given by this equation, of the particles becomes comparable to the inner particle separation in the substance. In fact, there is a thermal de Broglie wavelength equation that allows us to calculate exactly the temperature at which this happens. Once the lengths are comparable, the wave functions of the atoms overlap, they lose their discreteness, and form the condensate. Now, let us look at the Schrödinger equation governing the behavior of electrons in superconductors. In this equation, the following part is the Schrödinger equation of an electromagnetic wave, where A is the potential and phi is mass over lambda multiplied by e to the power of I multiplied by the phase of the wave, when simplified in one dimension. These last two terms here represent the repulsion of the electrons in the Cooper pairs. This equation is a bit different from the one we had derived in class because this wave represents a Cooper pair, especially at very low temperatures, which flows like a wave around a potential A that arises from impurities in the material. Normally, these impurities would create resistance, but at cold temperatures and with Cooper pairs, the electrons can go past these impurities easily without losing energy. Because A is a vector potential, it represents the electric and magnetic fields through Maxwell's electrodynamic equations and describes superconductors' tendencies to push out magnetic fields, which can allow it to levitate, as we have seen before. This is called the Meissner effect, and any magnetic fields that are passed through the superconductor are forced to move around it. The superconductor starts to act like a magnet with the same pole, which creates a repulsion and causes it to levitate. Now, with a superficial understanding of superconductors, let's look at some of their practical uses. One application of superconductors is in magnetic levitation, or maglev trains. Here, superconductors can allow acceleration to super high speeds, with low friction and super efficient locomotion. They levitate the train on a cushion of air, with coils on the side walls of the track to keep it centered. Superconductors are also used in MRI machines. In MRI machines, superconducting magnets are used to create magnetic fields that align the magnetic poles of hydrogen atoms. An additional magnetic field is then created, which momentarily displaces the magnetic poles. Once they realign and release their energy, an image can be created corresponding to the released energy. MRIs are capable of being used worldwide because superconductors are able to create large magnetic fields while having minimal heat output. Another application of superconductors is in particle accelerators, where the strength of the superconducting magnet allows carrying out higher energy experiments. Superconducting radio frequency technology is what accelerates the particles to relativistic speeds. By shooting radio frequencies into specially designed cavities, the resonant frequency will build up and create electric fields with high amplitude. By coating the interior with superconducting material, the performance of these devices increases by a significant margin and reduces the overall demand for power. Despite all these applications, superconductors are still not widely used because they require extremely high pressure or low temperatures to exist, both of which lead to increased costs and difficulties. However, as we continue to discover superconductors that exist in less extreme conditions, their applications will continue to become more prevalent.